Now there is another type of circuit element combination which is quite common. It's different from the series combination. In fact, it's the dual to the series combination. As we've seen, the characteristic of a series combination that leads to our key series resistance formula are the following two facts relating the currents internally to the external current and the voltages internally to the external voltage. In these cases, the currents are the same as the external current and shared among all elements, and the internal voltages we add to get the final total voltage. There's another type, the dual type to this, would have kind of the complementary characteristics. In this case, we would have that the external current is the sum of the currents through the composing elements, and that the voltages that each element sees are just the externally applied voltage. To see what this would look like as an actual diagram in terms of a circuit, let's try to first think things through carefully what we're saying here. So now we're talking about a parallel combination. So for a parallel combination, it's the dual to the above. In that case, what we're saying is that the voltage for every single element is going to match the external voltage, and that that if I add the currents flowing through each element, that must match the external current. Now, to make something like this, let's consider the following. So I'm going to have my external terminal up here and down here, right? And I have to put some device inside this box where the components of my device obey the rules which I've just laid down. And so I want to put some resistors in here, right? But they all have to have a voltage from their top to their bottom that matches whatever the voltage is to these external terminals. Well, that means it sounds like they must be wired directly to these terminals. So let me try to indicate what that might look like. So I might have something like this, where this is R1. And then if I have a second resistor, I would put him over here, R2. So now you see the terminals of R1 and the terminals of R2 are wired directly to the external connection points. And so each of their voltages, in fact, will match that external voltage. If I want to use sort of the same terminal names as I had before, that would be C and E. Notice also that the currents indeed would add in this case, because the total current that flows out of this system down out through E, this external current, is going to be the sum of the currents that are flowing either through resistor R1 if it's carrying a current I1, and resistor R2 if he's carrying a current I2. Those two would have to add together to give me my final total external current, which I will call here I. So let's see now if we can determine the terminal characteristics for this kind of a parallel combination. Well, we know then that the external current, as we've just been saying, has to be equal to the sum of the currents I1 and I2. That follows directly from Kirchhoff's first law, right? Because the currents entering point E, for instance, are I1 and I2. The sum of those then have to match the final current leaving, which is I. Now, we can use what we know about our individual circuit elements. You might recall here, and I'll just put it in a little aside, that our basic relation here is that the upstream voltage of a resistor is equal to the product of its current and its resistance. In this case, if I want the current then flowing through I1, I would have to take its upstream voltage and divide it by its resistance. In this case, the upstream voltage of I1, right, of R1, I'm presuming my currents are flowing downward. So once again, I would have an upstream side and a downstream side on each of my resistors. The upstream voltage of I1 is the potential difference between E and C, the voltage going from E to C. But that is, of course, just my external upstream voltage for my overall device. So that would then equal, that's going to equal then, make this a little bit bigger here. Sorry about the jiggling around. That's going to equal the voltage going from E to C divided by R1. And I2, similarly, is going to be the upstream voltage across R2 divided by R2 to give me R2. So that's going to be V from E to C divided by R2. But now we can factor out the V from C to E. So that's VC from E to C times, here we have the inverse of R1, and here we have the inverse of R2. So that would be R1 inverse plus R2 inverse. And what I'd like you to notice next is that when I look at my equivalent element in here, that equivalent element has an upstream voltage, right, because the current's flowing downward, equal to this V from E to C. That's its upstream voltage, so this is V up times this quantity. So this is starting to look a whole lot like the a simple proportionality again between the current flowing and the upstream voltage. And this almost looks like the resistance equation, except the resistance equation always is V is equal to I times some resistance. So with a little rearrangement here and dividing by the sum of these R's, I can rearrange this into the standard form. V upstream voltage for this parallel combination, I have to divide by these R's, right, is going to equal I. And when I divide by this sum, to move it to the other side of the equation, that's the same as multiplying by its inverse. So it looks like R1 to the minus 1 plus R2 to the minus 1, the whole quantity then to the minus 1 power, which we could write again as I times some equivalent resistance. But now we have the equivalent resistance for the parallel combination. So for parallel combination, we learned that R equivalent, to get it, we take the reciprocals of each of the resistances and then invert those.